Let's continue our lecture in fluid mechanics with the topic rotating vessel. Now in this video, we will answer the example number 4 and 5 in our handout. So for our number 4, a closed cylindrical vessel is rotated about its vertical axis. The cylinder is 0.20 meter in diameter and has a height of 0.12 meter. It is filled with water at a depth of 0.1 meter and the rest is filled up with air. Letter A, what rotational speed is necessary for the water to just touch the bottom of the center of the tank in RPM? B, what is the maximum pressure at the bottom of the tank? C, if it is rotated at a speed of 285 RPM, determine the radius of the uncovered portion of the bottom of the tank. So we have here our cylindrical tank, closed cylindrical tank with, okay, so let's put it here. Given the dimension 0.2 meter in diameter, so 0.2 meter in diameter and height of 0.12. Okay, so 0.12 meter high and that is 0.2 meter diameter. Then our rotational axis. Rotational axis vertically. So we're looking for omega, or the rotational speed or the angular speed. It is filled with water to a depth of 0.1 meters. So our water is up to this point here. That is our depth of water. Oops. 0.1 meter. No. The 0.1 is here. 0.1 meter and this is 0.02. And this is the filled with air. The depth of this is the height wherein it is only filled with air. Okay. Now for letter A, what rotational speed is necessary for the water to just touch the bottom of the center of the tank? So the rotation will cause the water to just touch the bottom of the tank. Here. Now when that happens, since this is a closed container, so we will have an imaginary line here. Why there is an imaginary line? Because that is the assumed height that the water can reach when you rotate it at that speed. So we have an imaginary height there, and let's use a broken line for that. Now when that happens, we will see here that the diameter for this paraboloid form inside the tank, so this is the paraboloid form inside the tank, the radius there now is R1. Let's name that as R1. There is a new radius. So this is the radius from at this point to this point. So use another color for that. Okay. So this is the radius. So when this happens, for the total height of the paraboloid, so we will have it as y. Let's name that as y. Now for that condition, so for letter A, for vortex, just touching the bottom. For closed vessel, we have the formula y, this y here, for the total height of the paraboloid. So y is equal to the h. So the h here is given as this height of the container. So let's name that as h. So that is h squared divided by twice of d. This is the d here, the depth of the part wherein it is filled with air in the initial condition. So this is now equal to, y now is equal to 0.12 height of the tank, 2 times the height of the empty space, 0.02. Therefore, y is now equal to 0.12 squared times 0.02, 0.36 meter. So that is the value for y. Now, since we have the value for y here, for the total height of the paraboloid, we can now compute for the omega. So that is y is equal to omega squared r squared all over 2g. So y is 0.36 equals omega squared. The radius, so what's the radius here? The radius here is 0.1. So that's the radius meter. So 0.1 squared divided by twice of gravity. So omega is equal to square root of 0.36 times 2 times 9.81 all over 0.1 squared. So that is 26.58 rad per second. And then we will multiply that with 1 RPM divided by, or that is 1 RPM in every pi over 30 rad per second. So that is cancel rad. So what's now our omega in RPM? Our omega now is 26.58 times 30 divided by pi. So that is 253.82 RPM. So that's for letter A. Now for letter B, what is the maximum pressure at the bottom of the tank? Oh, there's another solution. I remember there's another solution for this letter A. We will use the condition of the air. We will use the initial air volume, which is equal to the final air volume. Remember that this is a closed container, meaning there is no spilled water out of the container. So we will compute here what will be the initial air volume and the final air volume. So there is another solution. So let's put it, or we will use the condition initial air volume is equal to the final air volume. So for the initial air volume, this is the volume, and that will be the volume of cylinder. And then for the final air volume, so this one here is our final air volume, is it's the volume of paraboloid. So for the volume of cylinder, we have there pi, the radius r squared, and then depth of the cylinder filled with air, 0.02. Because the volume of paraboloid is 1/2 pi, the radius, that is r1 squared. So that's the radius of the paraboloid here, r1 squared, times the height, which is the height of the container, 0.12. So we can get the value for r1. For r1, we have square root of, so we will cancel here the pi. Okay, cancel pi. So that will be square root of 0.1 squared times 0.02 times 2 all over 0.12. So so radius is 0.0577. 0.0577 meter. Then using this R1, and we have here our paraboloid, we can now solve for y, or say h. So h is equal to omega squared r1 squared all over 2g. So that is 0.12 equals omega squared, r1 is 0.0577 squared all over 2 times 9.81. So we have now omega squared is equal to so that is 26.59 rad per second. So 26.59 rad per second, and multiply that with 1 RPM is pi over 30 rad per second. Cancel rad, so we now have omega is equal to 26.59 times 30 over pi. So 253.92. 253.92 RPM. And this is the same with the answer we got from the first solution. So they are the same. It's just that there's a small discrepancy with this one. Okay, so that's for letter A. For letter B, what is the maximum pressure at the bottom of the tank? So for maximum pressure at the bottom of the tank, of course, we will take the initial condition. So it's asking for the pressure here at the bottom of the tank. So pressure, if we're solving for force, that will be gamma volume. So for the pressure at the bottom of the tank, that will be something like this, right? The uniformly varying load. So what is the value of P here? For the value of P, so for letter B, P max, that will be gamma H, or the H here is the maximum. So what's the maximum height? So since we are getting the maximum, so what we can see here is it's not this the maximum height. What is the maximum height that the water can attain? That is the when it is rotating. So when it is rotating, the height of the water reaches this point, and this height of the water is the y of the paraboloid. So the distribution of the pressure is from 0 here, from 0 to maximum at the bottom. So our H max therefore is equal to 0.36 meters. So P max is equal to 9.81 times 0.36, that is 3.53 kilopascal. 3.53 kilopascal. That's for letter B. Now for letter C, what's the condition for letter C? If it is rotated at a given speed of 285 RPM, determine the radius of the uncovered portion of the bottom of the tank. So there is a rotation here given the rotational speed. So what is R2? There's going to be a second radius, and it's in the part of the uncovered portion of the tank. So that is the height. This is our H. So H is equal to 0.12. This is our 0.02. This is our 0.1. And because of the rotation here of given omega 285, was it 285? Yes, RPM. So 285 RPM. We will have for the parabola. Okay, so why is it that we are drawing it this way? Because 285 is greater than 253, the one we solved a while ago. So since at 253 RPM, so at 253 RPM, the water touches the bottom of the tank. Therefore, greater rotational speed will cause an uncovered portion at the bottom of the tank. That's why we will have this kind of drawing. So this excess paraboloid at the bottom of the tank indicates that the radius formed here. Okay, so there is going to be a radius formed here as the radius of the uncovered portion of the tank. So this is R2. Let's name this as R2. This portion here to here. And a while ago, this is our R1. This part here. This is our R1. This point, this point. So since this is going to be imaginary, because let's put imaginary line here, and also this part here is also an imaginary paraboloid. And since we have an excess paraboloid there at the bottom, let's name that as H. The height there as H. So there will be a total height of paraboloid as Y. Let's name this total height as Y. And the height of this excess here is H. So how do we solve this kind of problem? So having the radius here, given the radius here as 0.1. So we have 3 radius. The radius of the total paraboloid, the radius here of this paraboloid here, and the radius of the smaller paraboloid. So we will use the V air initial equals V air final. So volume of the air initial will be the cylinder there. And then the volume final will be this portion here, total paraboloid, minus the smaller paraboloid. Okay, so that is paraboloid this. So paraboloid here minus this one here. That will be the final air volume. So for initial air volume is the cylinder pi 0.1 squared times 0.02. And then for the final air volume is the volume of the bigger paraboloid. So 1/2 pi r1 squared times the height there is 0.12 plus h minus the volume of the smaller paraboloid at the bottom of the tank is 1/2 pi r2 squared, and that is h. What are we looking for letter C? What are we looking for? If it is rotated at a speed of 285 RPM, determine the radius of the uncovered portion of the tank. So remember that we're looking for R2. So we're looking for radius 2. Okay. So let's cancel all pi here. So cancel all pi. So what is 0.1 squared times 0.02? Then times 2. Yeah, that's times 2 for the squared here. So 0.004. So they all have 1/2. So we multiply it with 2. that will be 4 times 10 raised to negative 4 equals 0.12 r1 squared plus r1 squared h minus r2 squared h. So this is equation number 1. So here we can see 3 unknowns, r1, h, and r2. So there's 3 unknowns there. So we need to reduce the unknowns as possible. So let's find the let's use the squared property of parabola so that we can reduce the unknowns. So by squared property, so by squared property of parabola, that would be the bigger radius, the r squared, all over the total height. So the bigger paraboloid, the radius of that is 0.1, and then we have the total height y. So r1 squared and then y equals the much smaller one here, the paraboloid here, that will be r1, and then the height of that one is this. Okay, so r1 squared all over, so that will be 0.12 plus h equals the paraboloid that is smaller at the bottom of the tank, that will be r2 squared all over h. So let's find the values for y. Since this r here is already 0.1, so find y. Let's use the formula there for the angular speed. So at angular speed equals 285 RPM. Let's multiply that with pi over 30 rad per second divided by 1 RPM. So cancel RPM. So omega is equal to 285 times pi over 30. 29.845. 29.845 rad per second. So y now here is equal to omega squared, so 29.845 squared. The radius 0.1 squared divided by 2 times 9.81. So we can now have the value for y as 29.845 squared times 0.1 squared times 9.81. So 0.45 meter. 0.45 meter. Then going back to this squared property of parabola, we can now input there the r. So 0.1 squared all over 0.45 is equal to r1 squared plus h is equal to r2 squared h. So we can have formulas here. So concentrating here, we will have r1. So r1 squared is equal to, so 0.1 squared times 0.12 plus h all over 0.45. So R1 squared is equal to 0.1 squared times 0.12 over 0.45. 2.67 times 10 raised to negative 3. So 2.67 times 10 raised to negative 3 plus 0.022 each. So this is for R1. Next, let's concentrate at here. The concentration here is this and this. Okay, so that's equal to R2 squared is equal to 0.1 squared each all over 0.45. So R2 squared is equal to 0.1 squared over 0.45. So 0.022 each. So these are, then substitute to 1. So this is our first equation. So we will substitute all this to this equation. So 4 times 10, so that will be let's put it here. So substitute 1. So 4 times 10 raised to negative 4 is equal to 0.12 R1 squared. So 0.12 R1 squared is 2.67 times 10 raised to negative 3 plus 0.022 each plus, so for equation 1, plus R1 squared each. R1 squared each, that will be 2.67 times 10 raised to negative 3 plus 0.022 each times each. Then plus minus R2 squared each. So minus R2 squared each. So 0.022 each times each. So that will be 4 times 10 raised to negative 4 equals 0.12 times 2.67 times 10 raised to negative 3. That is 3.204. 3.204 times 10 raised to negative 4 plus 0.12 times 0.022, 2.64 times 10 raised to negative 3 each plus 2.67 times 10 raised to negative 3 each plus 0.022 each squared minus 0.022 each squared. So we will cancel these two here. So what's now the value of h? H now is equal to 4 times 10 raised to negative 4 all over 3.204 times 10 raised to negative 4. No. So 4, it's not. So 4 times 10 raised to negative 4 minus 3.204 times 10 raised to negative 4 all over will be 2.64 times 10 raised to negative 3, and then 2.67 plus 2.67 times 10 raised to negative 2. So the answer here is 0.015 meter. 0.015 meter. Then substitute this h. Remember, we're looking for R2. So R2 is here. So substitute it to, let's name it 2. Substitute h to 2. So R squared is equal to 0.022h. So 0.015. R2 now is equal to square root of 0.022 times 0.015. So 0.018. R2 is 0.018 meter. Yan. So that's example number 4. So this is 4. This is letter A. And then this is the alternative solution. The initial air volume equals to final air volume. This is letter B. C. Okay. So let's go now to example number 5. A closed cylindrical vessel, 1.2 meter in diameter, 1.8 meter high, and two-thirds full of water has a small hole at the center of the top cover. Compute the maximum and minimum pressure at the bottom of the tank if it's rotated at 90 RPM. So, again, this is a closed cylindrical vessel. This is our rotational axis. So it says there it is 2/3 full of water. So 2/3 full of water here. So this is 1.8 meter high. And the diameter is 1.2. 1.2 meter diameter. It's 2/3 full of water. So this is 2/3 of 18. So 2/3 of 18 of 1.8 is 1.2. So this is 1.2 meter. Therefore, this is 0.6 meter. Okay. And then compute the maximum and minimum pressure at the bottom if the tank if it's rotated at 90 RPM. So given our omega as 90 RPM. So given the rotational speed of 90 RPM. So what will be the drawing now for the parabola? So we cannot assume that it's going to be equal. So we will just put it this way, and there's going to be an imaginary line here. That will be the imaginary line. And imaginary curve. So our height, so we will have here a radius. There's a radius formed here, and of course our original radius, the height of the paraboloid inside, and what's the height here, total height. So there's going to be another height here for now we're going to look for the minimum and maximum pressure at the bottom of the tank if it is rotated at 90 RPM. So meaning, to find the maximum pressure, that will mean that this is the location of the minimum pressure wherein the height is lower. This is the lowest height that the water can attain while it's being rotated. And this is the maximum height that the water can attain while it's rotated. Therefore, we need to find the value of H here and the H of this, total H here. So we will name that as, so we will need to look for the height there. So this is the height of the paraboloid. Let's name that as H1. And this will be the H2. We need the H2 for the minimum pressure. So for the P minimum, we need the gamma H2. Now for the maximum pressure, so let's name this paraboloid here H. And this is the H3. We need the H3 for P max, gamma H3. So this is the 0.6 meter radius, and this is for the radius smaller. This is R1. So we need this. What is the value of 90 RPM in rad per second? This is pi over 30 rad per second over 1 RPM. So cancel RPM. We now have W or omega. Omega equals 90 times shift pi over 30. So 9, that will be, well, simply 3 pi. So we can just say 3 pi here. 3 pi rad per second. This, therefore, we have H equals omega squared, R squared, all over 2G for the H here. So what we're solving here is this H, this paraboloid here. Okay? So that's why we're looking for H. H is equal to 3 pi squared. R is 0.6 all over 2 times 9.81. So H is now equal to 3 shift pi squared So this is 3 shift pi squared times 0.6 all over 2 times 9.81. So 2 squared. I forgot squared. 1.63 meter. So we will use the squared property of parabola. So we're going to compare this parabola here with the smaller parabola inside. So that will be the radius 0.6 squared divided by the height of that parabola, which is 1.63, is equal to R1 squared all over H1. So R1 squared is equal to 0.6 squared over 1.63. So that will be 0.221 H1. So we will use that. That here in our V air initial equals V air final. And again, this is the volume of the cylinder of the empty. So that is 0.6 squared and the height is 0.6 equal to V air final will be the volume of the paraboloid, so 1/2 pi R1 squared times H1. Now this is shift pi times 0.6 squared times 0.6. So no, we will cancel the pi here now. Cancel the pi there. So we'll just remove the pi. So 0.216 times 2 times 2, 0.432. So 0.432 equals, what's our R2 here? R1 squared here is 0.221 H1. So H1 is equal to square root of 0.432 all over 0.221. So 1.4. H1 is 1.4 meter. Now since we now have the value for H1, so as we can see here, we can now get so since we have the value for H1, we can now get the value for H2. So H2 now is equal to 1.8 minus 1.4 is equal to 0.4 meter. Therefore, P minimum is equal to gamma H2 is equal to 9.81 times 0.4, that is equal to 3.924 kilopascal. And for H3, we can get now the value for H3. So this is our H3. H3 is equal to H plus H2. So H3 is equal to H plus H2. That is equal to H is 1.63 plus our H2 is 0.4. That is equal to 1.63 plus 0.4, 2.03 meter. Therefore, P max is equal to gamma H3, 9.81 times 2.03, that is equal to 19.91. So 19.91 kilopascal. So that is our P minimum and P maximum. So that's question number 5 or problem number 5. Okay, so that ends our video.